All right, today we're going to talk about quadratic functions and kind of the fun stuff that comes with that. What's a quadratic? Kind of what it some of the properties are and that sort of stuff. So a quadratic function is any function of this form: ax squared plus bx plus c. Note that only a is not allowed to be 0. So this does allow for some of the following things. Like we could just have like 3x squared or negative 7x squared plus 2. Like those are still quadratic. Over here up in the blue, I make this note that it's basically any function with x squared as its highest power. And we're going to get into more of the graphing of quadratics and stuff like that in the next few videos and such like that. But really, quadratics kind of just look like concavity. It looks like this, and it looks like this. And they're used to find concavity, and we're going to see that in a little bit. So the degree, so this is just, these two things are just in general, not necessarily for quadratic, but the degree of the function is determined by the highest power of x, and all quadratic functions have a degree of 2. So the highest power in quadratic functions is 2. It has to have the 2 for it to be quadratic. And then lastly, the leading coefficient is just the coefficient of the term in a function with the highest power. So whatever the highest power is, whatever the coefficient there is going to have the leading, or going to be the leading coefficient. So looking at this, because it's always good to just apply it, what we want to do is name the degree and the leading coefficient. So I'm just going to write D and then like LC. So looking at number 1, or this first one, I could see that my highest power is 2. Let's talk about one other thing real quick. If I have just an x, so we can remember that that's really just x to the first, and a number is really just x to the 0th power. We don't ever really think about that, but that is the degree. So any case, the degree in this function is 2. 2 is our highest power, and then that coefficient here is 3. So looking at g of x, the second one, we almost have the same exact function, but we can obviously see that it is written slightly differently. We see that this 3, not a b, d, is our highest power, and that coefficient, the thing that's multiplying that x with the highest power, in this case is 8. And then over here we have a similar situation where it's not really in descending order from high to low powers. Our degree over here, the highest power is 7, and that leading coefficient, whenever you see a negative, that negative goes with that coefficient. And if there's no coefficient, we can really just think of this as 1. So our leading coefficient in this case is negative 1. So this is going to become this idea with degree and leading coefficient. This is going to be a staple in the next month and a half of class or so. Working with it, learning about it, how does it interact, how can we determine shapes of functions using it. It's going to be a huge staple moving forward. Now, this is probably the trickiest thing about quadratics, and that is that quadratic functions have a constant second difference, as I'm going to mention it. The way that AP is going to mention a lot is the rate of change of the rate of change. So another way to think of this idea is the rate of change of the slopes. So in quadratics, the slopes are obviously changing. It's not one straight line. It changes over time. You know, it starts negative, then 0, then positive, and such. But the fun fact about quadratics is the rate at which the slope changes is constant. And we're kind of going to look at what that means in this question down here. So this constant rate of change is seen in equal length intervals. So for example, down here, we can see it's not going 1, 2, 3, 4. It's counting up by 4s. That's an equal length interval, so it's fine. So looking at this example and using this, we're going to talk about how to attack this problem. This is a super common problem. I can almost guarantee it was on the AP test last year. There's so many different problems that are built around this idea. So it tells us that this function is a quadratic function, and what we need to do is fill in the table. So it's going to look weird the first time around when we do it, but we're going to understand kind of what's going on afterwards. So what we're going to analyze is the rate of change. So basically, what is the bump, or how much do I increase or decrease as I go from value to value? And then the second thing we're going to look at is the rate of change of rate of change. So it looks kind of weird. It is a little bit weird, but we can go ahead and solve. So how do I get from 24 to 31? I'm going to add 7. So I'm going to also make sure to add the plus sign in here. And then how do I get from 31 to 35? And that's I add 4. So that's just saying like, oh, here's the average rate of change over this interval. Now, what the quadratic will tell us is when I look at the difference between 7 and 4, the rate of change of the rate of change. So how the rate of change between 7 and 4 is, I'd say I'm going down 3. How do I get from 7 to 4? I go down 3. So the other thing I know is when I want to go fill in this, etc., is that this jump here is also going to be minus 3. So I know that this jump is going to be plus 1. So my value here is 36. So it's kind of weird. But this is how we do it. The next jump would be minus 3 again. So that rate of change would go down by 3, so minus 2. And then 34. I'm going to go down 3 again. So I'd go to minus 5 and 29. Now, going backwards is slightly trickier. I know to go from here to here, I'm going to subtract 3. So when I go backwards, I technically have to add that 3 back. How do I get from something minus 3 equals 7? Well, that would be 10 to get from here to here. So I need to go subtract 10, essentially. So I'm going to get 14. And we could just check this last one over here just to reaffirm. Once again, I'm subtracting 3, so that means that this jump would be 13, and that makes sense with what I have here. So plus 13, plus 10, plus 7, plus 4, plus 1, minus 2, minus 5. So this idea is tricky. It's not the easiest thing in the world. We're going to do lots of problems with it to practice with it. But what we can notice here is that second rate of change, the rate of change of rate of change is constant, as I say. It's always minus 3, minus 3, minus 3, minus 3, minus 3, minus 3. That's the part where the quadratic function plays into it. I know that the rate of change is constant. So this is the information I know, and I can use this information to influence this. And then I use the rate of change, the normal one, to influence my actual function values. So we're going to do a very similar thing in this next question, where I basically find the average rate of change of the intervals. I'm going to do one of them all the way out just to kind of show you that, you know, we could do this in a faster way. So, oops, let's do it like this. So so I want to find the average rate of change over this interval. So I could do f of 0 minus f of negative 1 over 0 minus negative 1. F of 0 is this point, so that looks like 7 to me. So 7 minus 14, and then over 1. So I'm going to get negative 7 over 1. So the one thing that you're going to notice is that all these intervals are the distance of 1. So really, all I have to do is look at how far down or up do I go to get this next point. So I really don't have to do this average rate of change formula every single time. I could look between 1 and 0 and just see how far down I go. So, or 0 and 1. So I go down from 7 to 2. So that would be minus 5. 2 to 1, you can see I go down 3. 2 to 3, you can see I go down 1. Then I start going up 1. Up 3. Oops. Up 5. And then lastly, up 7. So now the next question, so that was finding the rate of change over these intervals. Average rate of change on each one of the intervals. The second question says find the rate of change of the average rates of change. So this is saying find the rate of change of the rate of change. Here's our rate of change, and I want to find the rate of change of it. And we can see from each one of these, I keep adding 2. Here, 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 I keep adding 2. So I would say rate of change of average rate of change is 2. Now, obviously, we learned about concavity already. So when we answer this question, we can obviously say it's concave up. We know that it looks like a smiley face, but how does this support your answer in part B? Concave up tells us our rate of change is increasing, or it's positive. Or we could say, well, let's say concave up means, let's do this in capital, rate of change is increasing, hence positive 2. Or I could just say like in part B. So you were still using the same idea that we did in the first question about the looking at the rate of change of the rate of change. It's just, you know, hey, can we transfer it into a slightly different situation and format? And that's essentially the skill that we're going to need to do for the AP test. The math, nothing that I did math-wise was difficult there. Not one lick of it. I literally counted down. But the framing of the question was different, and that's what makes it tricky. That's what we're going to see with the next few. So this is talking about, we got 3 more questions, and they're kind of more AP style. It's talking about linear and quadratic functions. So we talked about linear functions last video, quadratic functions today. But we're going to go ahead and do this together. So first of all, it says h is linear. So I know this is a linear function, so I know it's a straight line. But I want to know what the value of 15 is. So if I like draw up another square, I want to know what 15 is. Which is a little bit tricky because if we look at our table, it kind of jumps up by, it goes by 4 here, and then it goes by like plus 8. So it's kind of weird. But the one thing that we know about linear functions is that our rate of change is constant. So if I can find the rate of change over 1 unit, I could use that idea to get from here to here. So what I need to do is take the average rate of change somewhere. So I could do h of negative 4 minus h of negative 8 over negative 4 minus 8. Minus negative 8. And I could get h of 4 would be 17 minus 23. All of that over positive 4, which makes sense because when I get that result, what am I going to get? I'm going to get 6 over 4 negative, so negative 3 over 2. So what does this represent? This is just my slope. That's my slope. So now how do I use this to get this number? Well, what I could do is I could just say, okay, how many steps did I take? What's 15 minus 4? It's 11. So I take 11 steps to get from here to here. So what I need to do is take 5 times 11 steps of negative 3 over 2. Or not 5 times, excuse me. 5 plus 5 plus 11 steps of negative 3 over 2. And that will give me my answer. So I'm going to do this up here because that's where I have space. So 5 plus negative 33 over 2. Now, obviously, that's not one of my answers, so I'm going to need to simplify a little bit further. So 10 over 2 plus negative 33 over 2. That's going to equal negative 23 over 2. And we can obviously see that that's B as our answer. Cool. So it's kind of similar to what we did last time, low-key, where we're kind of just using the idea about rates of change, and we're making a quick calculation and being able to solve. So next, okay, looking at 15, we can see one major thing is that we are dealing with a quadratic function, which means that our rate of change is constant. So that's going to be important. I want to find what g of 8 is, and 8 obviously isn't in our table. It's going to look quite similar to this problem here. In the way that we do that. So I need to draw up my next couple x values of 6 and 8 here. And what I need to do is I need to analyze the rate of change, and then the rate of change of the rate of change. I hate when it does this. So yeah, let's go take a look. So my rate of change here is going to be, to get from negative 5 to 1, why does it keep doing that? I don't want to edit the freaking screenshot. Plus 4, and then from negative 1 to 0, I add 1, not 4. And now we can look, how do I get from 4 to 1? Is I'm going to subtract 3. So I know that this next jump here is going to be minus 3. So I can tell that that rate of change is going to go from positive 1 to negative 2. So I go from 0 minus 2 equals negative 2. And then I know that this jump here would be minus 3. So instead of minus 2, I'm going to subtract 5. And so negative 2 minus 5, negative 7. So that is my answer D. And we are good to go. So this whole idea of like finding the next couple values is going to be persistent, and that same idea is going to kind of persist in the next question. Now, this is definitely the trickiest one of the day. Definitely the trickiest one of the day. So, the function p is given by g of x plus 1 minus g of x. And it tells us that p of x is 2. So it tells us that whatever this crap is always going to equal 2, no matter what. Which of the following statements is true? And it gives us stuff about, like, b's positive and constant, what happens with g. So we could either be positive slope, concave up, increasing, or it can be both 1 and 3. So what we really need to do is analyze whatever the heck this is. And let's kind of just look at what it looks like. So these are two y values, okay? G of x and g of x plus 1, those are two y values. So the way I like to think of x plus 1 as a y value, it's basically this is a y value, and this one is the next y value. So, like, if I were to go up and use this graph as an example, like, this could be g of x, and this is g of x plus 1. Or, this is g of x, this is g of x plus 1. It's basically saying the next y value. So, looking at that, it's basically saying the next y value minus the first y value is 2. So, what can we gather from this? It's basically saying the next y value minus the original y value equals 2. So, we could gather a few things. Essentially, it's always going up. Because if I just draw some some plot. It literally doesn't matter. You can think of these boxes as one unit. This is my original y value, and I add 1 because I know that if I add 1, so go 1x value over, I need to go up 2. So this is y plus, or excuse me, these are x values. X value, x plus 1. That distance, that jump needs to be 2. And then that next one also has to be 2. You could think of this again as this one's the x value and this is the x plus 1. So it's the next one, and it goes up 2. So what shape does this make? It's a linear line. It's kind of difficult to conceptualize because we haven't done too much work with this, and this will come later on. So the graph always has a positive slope. It's always going up. We know that essentially the rate of change is 2. And then because it's positive, we know it's increasing. So the answer is D. Now, the other way to think about this, which is a little bit hard to see at first, is that this could potentially be looked at as the rate of change function, where, like, I could look at it as f of b minus f of a over b minus a, where b equals x plus 1 and a equals x. So on the bottom, what would happen is I'd have x plus 1 minus x. So what would happen? This x would cancel out, that x would cancel out. So essentially, this is just saying that the rate, this is like the most fancy way to say that, like, my rate of change is 2. It's a super duper fancy way to say my rate of change is 2. Like I said, there's nothing in this math that's crazy. It's just deciphering the way that they're displaying it. It's really difficult, I'm not going to lie. So let's just review our answers. Because p is positive and constant, we could say that it's positive slope. Our rate of change is 2. And because p is positive and constant, it's increasing. Well, it's positive, so I know it's going up. I can't say that the graph is concave up because I know it's linear, and as we learned in the last video, linear lines have no slope, or excuse me, no concavity. So that is it for today, talking about the quadratic functions.